Welcome back to our mini-series on measurement-based quantum computation. Today is part 3 on probabilistic heralded entangling gates. So, technically speaking, today's lecture will be much simpler than the last one you suffered through on fault-tolerant quantum computation. But even though the idea is simple today, it is of large practical importance, and we want to see why in a moment. Okay, remember from the first lecture that the two-dimensional cluster state is a universal substrate for quantum computation. Any quantum computation can be implemented on it just by 1-qubit measurements. But what if this resource state is faulty? That's what we want to look at today, and we want to look at that in a particular way, namely if this cluster state was made by entangling gates that sometimes fail and sometimes succeed, and they tell us when they fail and when they succeed. So that's quantum computation with probabilistic heralded gates. Okay, so why care? Why is this an important topic? This is relevant for quantum computation with photons. There is now a standard scheme of quantum computation with photons. This is the KLM scheme. KLM after the names of its inventors, Knill, Milburn, and Laflamme. And what this scheme supersedes is an earlier scheme of quantum computation with photons that uses Kerr nonlinearities. So what's the problem here? Photons, they don't like to interact. They just fly by one another without one photon caring about the other. They go through one another, and that's of course not good for quantum computation. You need interaction to have computational power. And in the old scheme, this interaction was brought about by using so-called Kerr nonlinearities. But these nonlinearities are rather weak in nature, and so it's not a very practical scheme. KLM improved upon that. So what they did is they introduced the nonlinearities that they needed by way of measurement, by way of photon number resolving measurement. Still, that scheme is rather costly, and here's where measurement-based quantum computation comes in. So it significantly reduces the operational cost of running KLM. Okay, so let's first look at why probabilistic quantum gates, even heralded such gates, why they can be harmful. So what you see here in this picture is a quantum circuit, just a sequence of quantum gates. Each one has a constant probability of failing. So even if most gates succeed, eventually one will come that fails. And then once this happened, you have completely ruined your circuit. So you need to start over. And if your circuit is very long, then the success probability for this circuit, that is the probability for no gate failing, is exponentially small in the size of that circuit. So you become exponentially inefficient and your potential advantage of quantum computation is gone. So this is bad. You need to find a more clever way of using these heralded entangling gates. And here is where the cluster state idea helps you. So we are looking at this now in the special case of 1D cluster states, just to simplify the analysis. Okay, so what you do is you use your entangling gates, your heralded entangling gates that sometimes fail, to not to directly in a quantum circuit, but to extend a cluster state. And this will sometimes fail, sometimes succeed, but under the right conditions, it will succeed on average. So what you have on that side of the cluster is wiggling back and forth. Sometimes you lose, sometimes you gain. On average, you gain, and that's good enough. So now to the other end of the cluster state. So this is where the measurements happen that drive the computation. Yeah? So there you are reducing the cluster state again, but you are processing the quantum information. Yeah? You are driving your computation forward. And so the bad thing that could potentially happen is that while you're doing the measurements, there's no cluster left to go to. Well, that is easily avoided by putting a safety margin between the two ends. Yeah? You are growing on one end, you are reducing the cluster state on the other, and you have the safety margin in between. So that's all you need. Yeah? And this is the basic idea. This is how you reduce the computational cost of KLM. It's actually a couple of orders of magnitude. So now let's get a little bit more technical, even only very slightly. So here is two useful facts about quantum computation with cluster states, or about cluster states mainly. And we have already seen those facts in lecture number 1. So the first fact is about growing a cluster state. So we have seen that cluster states are made by the Ising interaction. And in terms of gates, this is conditional phase gates. So we put a cluster qubit there in an eigenstate of sigma x, and we connect it by a conditional phase gate, and we have grown our cluster state. So this is fact number 1. Now fact number 2. We can also cut cluster states, namely by making Z measurements. So when a Z measurement happens, then that qubit is removed from the cluster with all the edges that end in that particular site. So in the example that you see here, you have a 1D cluster state, and the Z measurement just splits it into 2/2. And this splitting really leads to a disentanglement between the left and right. So now, how are we going to use these facts? So first fact, well, the situation that was previously described applies when the conditional phase gate, the heralded phase gate, when it succeeds. Yeah, then the conditional phase gate is really implemented and the cluster state is grown. So in that good situation, we increase the size of the cluster state by 1. Now, second scenario, the gate fails. We get a failure message reported, and we don't know really what happened, but we know that the entangling gate has somehow messed up. So now we can use our Z measurement like a pair of scissors and cut off this faulty segment of cluster state. So we are losing the qubit that was appended, or that we wanted to append. We are losing the qubit from which we have been trying to stitch on, and we are losing the qubit that we had to measure in the Z basis to cut off this faulty portion. Okay, so this means rather than extending the cluster state by 1, we are reducing the size of the cluster state by 2. Okay, and now it's just a matter of probability to work out what happens on average. So, say our success probability for making the gate is P. Yeah? So then, well, with probability P, we are extending the cluster state by 1. With probability, with probability 1 minus P, we are reducing the cluster state by 2. And so the change of the length of the cluster state on average is given by this formula here. Yeah? So you see the change in length is 3 times P minus 2. All right, and so what this means, if the success probability of the entangling gate is larger than 2/3, then on average, the cluster state is grown. Yeah, and so this is the basic idea. You need to be in this regime, then you win on average, and now all you need to keep is the safety distance between growing and using the cluster state. Yeah. Okay, so that was basically it. As I said, it's a very simple idea today, but useful. All right, but there is still this condition for what I explained to you. I mean, first, it was only in 1D. You want to apply this to dimension 2. And also, it only worked if the probability of success of your entangling gate was sufficiently high, namely above 2/3. Okay, but this was just to ease the explanation. It's not fundamental. And the more general case is left to you as a homework exercise. So now you want to know whether the answer that you come up with was good or not so good. So try for the following. Try to come up with a computational scheme of using these probabilistic heralded gate that is efficient in the size of the cluster. So making this cluster state with the probabilistic gate should be linear in the cost of making the state with deterministic gates. You will just have a constant in front, but otherwise this linear scaling. So that's one property that you might want to have. Second property you might want to have is you want a scheme that works for any non-zero success probability, not just probability larger than 2/3, but for anything larger than 0. So this is for you to try. Good luck. Okay, so this is now the end of today's lecture, and here you have a couple of references if you want to read up about the subject.